Alright, from the last video we proved that our grad squared E is equal to minus W squared over speed of light squared E. Now we want to go into the lossy dielectric. Now the lossy dielectric is more of an insulator that doesn't insulate properly, but it still conducts, but it doesn't conduct well enough to be a conductor. So it's an insulator that doesn't insulate well but doesn't conduct as well to be a conductor. So it means that there's actually a current because there's a source. So J is present. There's a charge. A charge is in the material, and charge is denoted by conductivity E. So in our formula for the new Maxwell we found, we can replace grad squared E equal to J omega mu to bracket conductivity E plus J omega epsilon E. Now we can factorize E out. So we have grad squared E is equal to J omega U conductivity plus J omega epsilon E. So this is the new equation. Now, does this look familiar? This is also a constant because the conductivity of a material is constant. The change of the electric field, or the change in the amplitude of electric field, is constant, and the epsilon of that material is also constant. Now this is not epsilon naught, this is epsilon here is equal to epsilon naught epsilon r, and our mu is equal to mu naught mu r. So we don't know what the material is. So this is our new, but this is a constant, so we can denote it as our, comparing it with our free space, it's going to be our y squared, or our propagation constant squared. So that means propagation constant squared is equal to J omega mu into bracket conductivity plus J omega epsilon. So this is our propagation constant squared. Now, normally we start the whole process again. So normally our propagation constant is a complex figure alpha plus J beta. Now, we didn't really talk about what the alpha and the beta is. The alpha is your attenuation constant, meaning that it loses power, or the amplitude reduces as it propagates by distance. Now last time alpha was 0 because hey, it's free space, so there's nothing that's going to absorb some of its power, so it just keeps going and doesn't attenuate. Beta is the phase change, so as it goes it changes its phase by that's the phase constant. It changes phase by a particular constant. So it's not, the entire wave is not exactly in phase, it keeps changing. Okay, so this is the definition of what we have there. So let's do y squared. So y squared is going to be alpha plus J beta squared, and that's going to be alpha squared minus beta squared minus beta squared plus 2J alpha beta. Okay. Now let's look at this. This is minus here. This is minus, and here's minus. Here's minus, and then remember from the equation, from the Maxwell equation, way up there, it was minus J omega U, so it's minus there. So going back down the lossy, we have this, so the minus cancel minus, leaving us with that plus that we had there before. Okay, just to correct a little thing there. So we compare what we have here to what originally y squared was, or our propagation constant was. So if we open that bracket, this is going to give us conductivity omega mu j. Now j times j is -1, so that'll be minus omega squared mu epsilon. Omega squared mu epsilon. So that is what you have there. If you look at it, it looks like the last one. So we see that this is our real component because it doesn't have a j, and this is our imaginary because it has a j. This is complex numbers. You can research on it more for more information. Now if we're to compare this, this is also going to be our real since there's no j, and it's going to be our imaginary since there's a j there. So therefore we have that alpha squared minus beta squared is equal to W epsilon. Alright, now let's find the magnitude of propagation constant squared. That's going to be square root of the real part, alpha squared minus beta squared, plus into bracket 2 alpha beta squared. Now remember what we got as our answer. The final answer was alpha squared plus beta squared. So if we now do the magnitude, the same thing we did there for this guy. If we do the same thing for this guy, so we need to find the magnitude of him. We do. Now we find our magnitude from the actual formula itself. So this is our formula, the imaginary plus real. So we find our magnitude using this. So we do imaginary squared plus real squared, all square root. So we get this squared is going to be the square root of W squared mu epsilon squared plus conductivity W mu. Right? Conductivity W mu. Okay. Now we can factorize W mu out of it. Factorize W mu out of it, we have give us the square root of W mu squared all into bracket W epsilon squared plus omega, or just this, conductivity squared. Now square root of this squared is going to be just W mu all square root of W epsilon squared plus conductivity squared. Okay, so I can decide to factorize WE out of it again. So if I factorize WE, I get this square root of W epsilon squared all into bracket 1 plus, now it's affect conductivity here, conductivity of a W, E squared all squared. So I just factorize it out, so you know that this is going to be WE squared and conductivity squared separately, but since they're the same thing, I'll just put it back inside. Alright, so we know we're going to have this. This would be W squared mu epsilon square root of 1 plus conductivity over W epsilon squared. Okay, so this is what we have. Now we equate it to alpha and beta. So it means this squared is also equal to let's put it here. So this and is also equal to alpha squared plus beta squared. Now doing simultaneous equation, we know alpha minus beta squared is equal to this. Alright, so we bring them together. Alpha squared plus beta squared equal to mu squared, omega squared mu epsilon square root of 1 plus conductivity over this all squared. And then alpha squared minus beta squared is equal to minus w squared u epsilon from this point here, the real part, real side. Alright, so now we do simultaneous equation, so we subtract. So if we subtract, we'll get 2 beta squared is equal to w squared this square root of 1 plus conductivity w epsilon squared, then everything plus w squared mu epsilon. So if we factorize w squared mu epsilon, we'll get b squared has 2b squared is equal to w squared mu epsilon, then all square root of sorry, not so large, just square root actually. Then that'll be into bracket square root of 1 plus conductivity over w epsilon squared, then not outside of the square root plus 1. So now if I divide by 2 and find the square root, so b is going to be, now square root of w squared is w, so I'll put w outside. W big square root of mu epsilon over 2, right? Mu epsilon over 2, then square root of, as into bracket, square root of 1 plus conductivity over w epsilon squared, and then plus 1. And so that is your b. But if alpha squared minus beta squared is equal to minus w squared mu epsilon, therefore alpha squared is equal to minus w squared and plus beta squared. And remember, beta squared is equal to, remove the square root, that's just going to be plus w squared mu epsilon over 2, and all into square root of, into bracket square root of 1 plus conductivity over w epsilon squared and plus 1. So now if I factorize w squared u epsilon, I'll get alpha squared is equal to w squared mu epsilon all into bracket all in the bracket minus 1 plus 1 over 2 okay, now if I open the bracket fully, I'll get minus this plus this over 2 square root of 1 plus conductivity over w epsilon squared plus w squared over 2. Now I just opened the bracket. Now you'd see that 1 minus 1 plus half will give us minus half, right? So that's minus 1. So if minus 1 plus 0.5 should give us minus 0.5, and that's equal to minus 1 over 2. So we have w squared. We got w squared ue 2 1 plus conductivity w epsilon squared minus w mu 2. Now we can factorize w squared mu epsilon over 2. If you factorize it, it's going to be w squared mu epsilon over 2 all in the bracket square root of 1 plus conductivity over w epsilon squared minus 1. Now if I find the overall square root, I'll get the same answer as B, just that I have a minus 1 instead of plus 1. That's the only variable, that's the only noticeable difference between both of them. Now you can see that you can still get back alpha is equal to 0 for free space. Remember that free space, we have J is equal to 0, therefore conductivity is equal to 0. If this is equal to 0, then you have square root of 1 plus 0, which is equal to 1. 1 minus 1 is equal to 0. That means everything you have here is equal to 0 for free space. So you can see that the formula is still correct for free space. And for your B, for free space, if here were to be 0, for free space, then you'd have square root of 1 plus 1, and that's going to be 2. Square root of 1 is 1. 1 plus 1 is 2. 2 cancels the 2 down here, and you have w square root of mu epsilon. So you can see that it's a kind of back and forth relationship. This is a derived formula for your alpha. Now take note, this is the formula you need. Your beta and your alpha for lossy. So you can see that this is more or less the general formula for any medium. If you have free space, your conductivity is 0, everything will be 0. If you have lossy dielectric, your conductivity will be more or less 0, very small, but it will still be existing. But for a conductor, then your conductivity will not be 0, and then you have another value here. So this is your alpha and your beta. This is the general formula for alpha and beta.